Okay, we're going to talk about section 14.3, Introduction to Sequences in Series. First part says a numerical sequence is an ordered list of numbers. So as you can see, there's your lists, 2, 4, 6, 8, 1, 1 half, 1 fourth, 1 eighth, whatever you have. That's just what a sequence is. It's just a list of numbers with some pattern to them. The term of a sequence is just an individual entry. So the first term, the second term, the third term are just individual entries for each of those. A finite sequence is a sequence that has a finite number of terms. In other words, it terminates or it ends. It does not go on forever. It's finite. So for example, this sequence up here, 1 square root of 2, 10 square root of 15, this would be a finite sequence since it doesn't continue on forever. An infinite sequence goes on forever. And that's usually noted by the 3 dots at the end, and this is something that would never terminate. For example, this one here would be infinite, and this first one is also infinite. Because of those 3 dots there, that means that it continues forever. A letter with subscript is often used to denote the various terms in the sequence. So for example, the sequence 2, 4, 6, 8, dot, 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 2n. A sub 1 just means the first term, which is 2. A sub 2 means the second term, which is 4. A sub 3 is the third term, which is 6. And so on, so that the nth term in this case would be 2n. Example 1, they give us an explicit formula. An explicit formula is something that contains the n in it. So it's based on which term are we dealing with. So for this one, all that I'm going to do is take that subscript, in this case 1, and plug that into my explicit formula for n. So it would just be 1 over 1 plus 1, in this case 1 half. For the next one, I'll take a 2 and plug it in. So it would be 2 over 2 plus 1. 2 thirds, plug in a 3, 3 plus 1. 3 fourths, plug in a 4. And we have the first 4 terms. Oh, sorry, not 4, 100. 100 over 101. Sorry about that. And that's how you would do a type of problem with it when they give you the explicit formula. Example 2, consider this sequence. Again, an explicit formula, negative 10 to the nth power. It wants the sum of the first 3 terms. What we're going to do is figure out the first 3 terms. In this case, it starts with n equals 0, then 1, then 2. And then I'm going to add those 3 together. So the sum of the first 3 terms, b sub 0, I just plug in a 0, plug in a 1, and plug in a 2 for n. So this would just be 1, negative 10, 100. And then it wants the sum of those terms. So I'm just going to add all 3 of those together, and that gives me 91. Moving on to recursive formulas. So recursive formulas are based on the term previous to it. So notice this has the equation here is not just doesn't just have an n in it. It has b sub n minus 1. What does that mean? It means it's the term before, because this is b sub n. The term before it, or the previous term, is b sub n minus 1. So that's the type of recursive definition. It is based on the previous term. Now you have to have been given b sub 1 and sometimes b sub 1, b sub 2, those first terms, in order to know where to start. So this one they gave you that b sub 1 is 4. And then b sub 2, I'm just going to use this formula. It's 2 times b sub, plug in a 2 here because I'm at b sub 2. b sub 2 minus 1 minus 1. Well, what does that mean? That's b sub 1 minus 1, but we know that b sub 1 is this term right here. So that's what I mean by recursive is based on the previous term. It's always going to pull up the term before it. So that's really 4 minus 1. When I work this out, I get 6. B sub 3 in the same fashion is going to now pull in b sub 3 minus 1, which is b sub 2 which is just 6. So it's the previous term. And when I work that out, I get 10. And then here, following that same pattern, I can bring in the previous term minus 1, and I get 18. And those are my first 4 terms. Example 4 wants us to find the first 5 terms of this recursively defined sequence. Now this one's interesting because it did define it for both 1 and 2. Because in the actual equation it goes back to the previous term, n minus 1, and then it goes back to 2 terms before, n minus 2. So they gave us 1 and 2, and then c sub 3 is going to take c sub 3 minus 1 over c sub 3 minus 2. Well, that's really c sub 2 over c sub 1. C sub 2 is just 2. C sub 1 is just 1. And so c sub 3, or the third term, is 2. Similar fashion, c sub 4 is going to go back to c sub 3 over c sub 2, which is 2 over 1. Whoops, I did that wrong. 2 over 2. And I get 1. And then c sub 5, it takes the previous term, which is c sub 4, over the term that's 2 before it, c sub 3. So that would just be 1/2. And these are the first 5 terms. This example just has you take a sequence and write it in a graph form. The thing you want to notice here is as I'm graphing these, I want to just graph them as dots, as ordered pairs. I don't want to connect them because it's just a sequence. It's just the list of numbers. It's not the numbers all between them, right? It's just those numbers. So if I plug in 0, 1, 2, and 3, and plug those into this explicit formula, 1 over 2 to the 0 is just 1. 1 over 2 to the first is 1/2. 1 over 2 squared, and 1 over 2 to the third. And so when I go to graph those points, 0, 1 will start up here. 1, 1/2. 2, 1/4. And 3, 1/8. And again, it's just those 4 points themselves. Do not connect them. This isn't a function. It's just a sequence. All right, let's turn the page and talk about sigma notation. This is a capital Greek letter. It looks like an E, but it actually is called sigma. It's used to denote the sum of the terms in a sequence. So notice here, it's all of these added up together. This bottom number, k equals whatever, that's your start number. That's what you're going to always start with. The top number at the top of your sigma is always your stopping point. So start with the one at the bottom, plug that in until you get up to the top and add them all together. So let's try example 6. Express each of the following without sigma notation. So I'm just going to plug in 1 for k, and I'll have 1 squared for the first one. And then plus, because sigma again is adding them up. It's the sum of all of these terms. So then I plug in a 2, 2 squared. Then I plug in a 3, 3 squared. Then I plug in a 4, 4 squared. And I have to stop when k equals 4 because that was my stopping point. So now I work this out. And that gives me 30. Do the same thing for the next one. Plug in a 1, plug in a 2, plug in a 3, and we'll stop at 3. So I plug in a 1, add it, plug in a 2, and then add it, and then plug in a 3. And then it's just a matter of working this out. So 3 minus 2, 6 minus 2, 9 minus 2, 1 plus 16 plus 49. And you get your answer. Same thing for C. In this case, you're going to have this variable x, and that x is just going to come along the whole time. So I start with 1. I'll have 1 times x to the 1 minus 1. Second term, 2 times x to the 2 minus 1. Third term, 3 times x to the 3 minus 1. Fourth term, 4 times x to the 4 minus 1. You can tell them to come in. They just have to be quiet. This one would, x minus 1 would just be x to the 0. which is just 1, x to the first, x squared, x to the third. And then this term is obviously just 1, and I can simplify. And so for this one, I do have a complete polynomial expressed out, and you just leave those x's in there. Okay, the last example. Notice that it's not k every time. It was k, k. This one time it was I. This is now j. So you can use different letters for those. So in this case, when it's k, j, I'm going to plug in a 1. So I'll have a sub 1 plus 1 minus a sub 1 plus a sub 2 plus 1 minus a sub 2. And then we got to keep going. A sub 3 plus 1 minus a sub 3, a sub 4 plus 1 minus a sub 4, and a sub 5 plus 1 minus a sub 5. Now the nice thing is a lot of these are going to cancel as we go through, because 1 plus 1 is the same as 2. 2 plus 1 is the same as 3. 3 plus 1 is the same as 4. And then 4 plus 1 is the same as 5. So in the end, what I have is negative a sub 1 plus a sub 6. I'm pausing.